Well, it doesn't trick it. Here we go. In case you are watching online, I rarely have nice things to say, but I do today. Thank you, sir. Yes. You knew you were leaving already? Oh, never mind. I thought you were packing up. Okay, here we go. Chapter 11. I want to be done with it by the end of the hour. So here we go. Vapor pressure. As discussed last chapter, vapor pressure is the pressure of a gas above a liquid. Liquid substances of low molar mass and weak IMF tend to have high vapor pressures. Why? This is an important little nugget right here. If they have low mass and weak IMF, why do they have high vapor pressures? Talk to your friends about why. Not me, your friends. Ready to go. All right, hopefully you got through that pretty quick. So the low molar mass means they're heavy and they'll stay lower. So like whatever, that's not as important. But weak IMF, that's the really important part here. It helps if you understand maybe this picture too. A low vapor pressure means there's not very many things above the liquid. A high vapor pressure means there's tons of the gas above the liquid. So things that do not hold on to themselves very strongly are more likely to have low boiling points, which means they have high vapor pressures. So like those are the things you smell quite a bit, like gasoline, and it's pretty big, but it has pretty weak IMF. You can smell gasoline. It's very has a very strong odor because it has a really high vapor pressure. It has evaporated into the environment. Paint thinner, what? Chlorine for sure. Sulfur gas, yeah. But usually when we smell sulfur, we're smelling hydrogen sulfide because it reacts with the hydrogen in the air. And this is what usually the smell is. But those things, those mean, those relate to boiling point and vapor pressure. So increasing temperature will increase vapor pressure. Why? We talked about this earlier, not today. But as you add energy, more of the liquids will be, the attraction between the molecules in the liquid will be broken. And if they're broken, then they leave. So as we add energy, we know we change the state, and it has to do with vapor pressure as well. Okay, let's watch this little clip real fast. I don't think it's the one we watched before.
We know that boiling is strongly influenced by atmospheric pressure. Pulled down by gravity, the air above us creates pressure, and that makes it difficult for bubbles to form and boiling to take place. We can think of atmospheric pressure as the collisions of air molecules against the surface of the water. That's the pressure. The more collisions, the greater the pressure. But water molecules can create pressure when they leave the liquid. As these faster moving water molecules escape, they collide with the molecules of air. This creates pressure, and we call it vapor pressure. In a way, the water molecules are pushing or colliding against the air molecules. This reduces the amount of pressure felt by the water. Back to boiling. Textbooks often state that when the vapor pressure equals the atmospheric pressure, boiling takes place. This is called the boiling point.
Okay, in the matching terms, right, Soraya? She said, Davidson, I don't really understand how the vapor pressure, the atmospheric temperature makes sense, and it's because it doesn't. The matching term that said boiling point and it related vapor pressure and atmospheric temperature. The word was supposed to say pressure. Do you know what I'm talking about? Right. It was just me being dumb. I need to check something real fast. I'm a little worried. Okay, I should be good. I plugged in that new test microphone.
Think of it
I'm
this way.
worried.
Atmospheric pressure pushes
Whoop.
down,
I need to
and that
shut-
makes it difficult for the water molecules to spread out and form a bubble. But when the vapor pressure increases, molecules from the liquid escape and they push against the air molecules and effectively reduce some of the pressure. This makes it easier for the liquid molecules to spread out, form a gas, and to rise to the surface. That's boiling. We can make boiling happen by either increasing the vapor pressure or decreasing the atmospheric pressure. Either way, once the vapor pressure and the atmospheric pressure are equal, we've reached the boiling point and boiling can begin. One last thing. Different substances have different vapor pressures, and therefore they have different boiling points. This has to do with how strongly the molecules are attracted to each other in the liquid. The more strongly they're attracted, the less the vapor pressure, and it's more difficult to boil. Therefore, the higher the boiling point.
All right. So, super chill video. I can barely watch videos in normal speed nowadays. Um, but it helps us get a little grasp of what that pressure is and how it's related to boiling. We don't have to have a super exact understanding of it, but we definitely need to know the stronger or the higher the IMF, the lower the vapor pressure, and the higher the boiling point. All right. And then vice versa. I'm not going to try and say it again because I'll throw everything and get confused myself. All right. And then make sure you realize that a high vapor pressure means there's lots of stuff above the gas. A low means there's a little bit of stuff beneath the gas. All right. Okay. Just a summary real fast of solids, liquids, and gases. Solids have lots of intermolecular forces, or the most intermolecular forces. Liquids are in the middle. They have some intermolecular forces. They're strong enough to sort of keep them attracted, but not so strong that the molecules can't move. That would be a solid. And then a gas, we have zero intermolecular forces. That was one of the definitions of an ideal gas, is the individual molecules had no interaction with other molecules except for elastic collisions where no energy was exchanged. I have no idea what this is, but it looks great. It does look great. All right. Next. Okay, we already talked about this. So we're in phase change land, right? Okay, did we talk about this table enough? Do you feel okay about it? All right, ice, liquid, gas, and the difference in energy. This is important because it's on your test for sure. It takes more energy to vaporize something because you break all intermolecular attractions. All right, then definitely 100% you need to know the temperature of a substance does not rise during phase change. Those are the two things you need to know for sure. All right, phase diagrams. These are really important. You need to be able to recognize two of them. Well, really it's one and then all the rest. And the difference is this line right here. Well, that was pretty good. And that wasn't. All right, this is the phase diagram for water. Whoops, water. This is the phase diagram for carbon dioxide, or really most everything else. The thing that is unique about water, once again, is this line versus the slope of this line. This has a negative slope. This has a positive slope. And water, we know, has a weird property where its solid is less dense. So it turns out we can make things melt easier with water with pressure versus the others. And we'll get into that. Whoops, phase diagrams. Phase diagrams show the relationship between temperature, pressure, and the state of matter the substance is in. The lines represent the boiling point and melting points under given conditions. So if we were to label this line right here, what would we call this line? It's either one of these two. So what do we have when a solid goes to a liquid? Or sorry, a gas. All right, that's sublimation. Deposition. Now, water for us doesn't normally do that, and that's because at normal, we're at ATM, right, and 25 degrees. So usually we're chilling here and life's normal. So let's go up to a normal pressure and temperature. All right, when ice goes to a liquid, we would call this line the melting. You don't have to memorize these if you just realize that you can look at the graph and interpret data. And then what do we call when a liquid turns to a gas? All right, boiling point. So a typical question will say, what segment represents the boiling point? And you would say A, D. Yes. Go ahead.
Yeah, so the typical point is that more theoretical or is it real?
It's real. You just have to get it under these exact conditions of 4.5 torr, so almost no pressure, and 0.0098 Celsius. And you can get those three to exist at that point. But that's like, we'll never experience that. We can't put our bodies under those conditions. So even though we know it would happen, it's also the same thing, a theoretical. If we created these conditions, this would exist. Pretty much. Like, it depends on your elevation. We're a little under.
Is that why, so for CO2 and even kind of water, if you actually were to get ATM way low enough, the low pressure makes it all spread out, so that's like gas?
Yep.
That's just weird because you don't usually see that. Usually that's all based on temperature.
Yeah. But they're definitely both 100% related.
Would you be able to do that in like a vacuum with water? Or?
Yeah, you need some sort of vacuum to get to 4.58 torr, which is a really, really good vacuum. And then you would have to get it to this exact temperature, which would be really hard as well. 0.0098 is, oh, I'm sure they have. I'm sure they have. All right, so understand that which piece of the phase diagram represents which state of matter. Then make sure you are comfortable on what the segments represent. There are some things on here that they might put just for labeling purposes. Oh, I tried. But usually they do mean something. So like B, what do you think B is called? It is melting point, but it's a specific name. Good, Grace, say it louder. That's your normal melting point. Why would we call it the normal melting point? Because it's at 1 ATM. All right, then letter C must be representing what? Normal boiling point. You could get away with calling it vaporization point too, that's fine. All right, A would be the triple point. It's where all three states could exist in equilibrium. It can happen. Once again, it has to be under these exact conditions, which are hard. I have no idea.
Let's see if we can find it on YouTube.
It is, what's that? Is there one? Of carbon dioxide? So what did it look like? Oh, that looks kind of boring. So it looks like a white blob surrounded by a liquid and clear air. Yeah. I feel like on Saturday in driver's ed, I feel like I drove through the triple point.
You drove on Saturday too?
Yeah, I drive every day. Why are you creeping on me?
What time were you driving?
all day long. 9 to 3.
You drive that blue car?
Oh, are you the van? Are you the van that harassed Cephalo while he was parallel parking? Oh, well, he turned in that license plate to the police, just FYI. Okay. All right. What do we call this? Critical point. It's where these two become indistinguishable. And a superfluid,
Yeah, after that point.
supercritical is what it would be called. It just means above. Yes.
How does that even work? Like, how can you not tell the difference between the liquid and gas?
I have no idea. Because look, this is at 218 times the normal pressure. Like the gas is so compressed that it behaves like a liquid, but it has no interaction. So that's a really valid question. How would it look? Okay, so oftentimes the AP test asks you to explain the process of dry ice and why it's called dry ice using a phase diagram. And it's really, really easy. You just look at normal pressure. Like if you're going to go buy dry ice at Smith's, you're buying it at basically 1 atm. And at 1 atm, liquid carbon dioxide does not exist. We have to be above 5 times. And 5 times might not sound that big a deal, but like that's extreme amount of pressure. All right, like 218 atm is off. It's completely off the charts. All right, so you would say on the AP test that dry ice is called dry ice because at 1 atm, carbon dioxide sublimates straight from a solid to a liquid, or sorry, to a gas. I hate when I'm an idiot. All right. We got those. Hey, that's it. So we need to describe the irregularities on the water phase diagram. So on the water, you have this, but you have just a little bit of that and that. You okay with that?
So the reason why we never find liquid carbon dioxide is what we just said is the pressure's like way too high for normal.
We'd have to have 5.11 atm to get liquid. All right, then a normal one looks something like this. All right, so it's this slope of this line. So water has a negative slope for its melting point, and everything else has a positive slope for its melting point. Yes, sir.
Are there any other substances that have negative slopes to their melting point? Or
Say that again.
are there any other substances that have a negative slope like that?
Yeah, not a ton. They would have to have, they'd be polar and have hydrogen bonding.
So like NH3?
Yeah, it's not as dominant, but probably also has that. Yes, Fabian?
Also make them less dense as a
Uh-huh.
solid.
That they should float. All right. Okay. That's chapter 11. Hopefully you enjoyed it. It kind of, I don't know, I was watching the Blue Planet 2
Oh yeah.
and watching the dolphins surf.
I love the guy's voice.
Yeah, David Attenborough. And like, we don't look at that very often, think chemistry, but we couldn't have a wave crest. That looks more like a duck, but whatever. All right, it doesn't matter. But you wouldn't have this happen without intermolecular forces. Yeah, they wouldn't stick together. So you'd have the energy move through, but even if the bottom slowed, which is what makes a wave crest, it would just lower the hill, like it would just fade out. If there was nothing, everything would be in the gaseous state.
So if water wasn't boiling, wouldn't it just be like the ocean would be like completely ice and like a few feet of water?
Yeah, if water didn't flow, we would not have life. It's one of the greatest miracles of all things.
Everything will be cold.
It would freeze, it would sink, it would never melt. Every year it'd get thicker and thicker, thicker. Eventually the planet would just freeze. The water
That's how
is by far the most important thing for our living human air breathing body.
So it's a really bad idea to make sinking eyes.
Sounds like something a villain would do in a Batman.
And then they would make it like so it's contagious, so it spreads.
Yeah.
They just like drop it in the fish and the ocean and now that you just kind of
I love when Doofenshmirtz makes the like attractinator or whatever, and then he reverses it on accident and shoots his only girlfriend he's ever had and she stops liking him. That's my favorite episode ever.
When men cried.
Oh, David, you didn't have, you know what David did to, what was it, second hour? He showed them something that they were gonna do, and he's like, now if Baby was in the class, he'd say, can this be the only thing we do on the test? He told that to his whole second hour, and I was like, wow.
You're welcome.
People listen to this at hour you weren't here once, so.
Yeah.
Um,
I mean, period, I guess.
I'm trying to open 13, but it's freezing. Okay. Your reader has information on 13 as well. 13's more math. It's not, I don't know. Well, it is. There's one part that's way hard. Yeah, well, okay, I lied. I've been trying to create the online test for you to practice over and over and over.
Like the online like AP test.
No, to just give you one on Canvas so you could review like I did. I'll show you what I mean. Well, I already have it here.
So how long is that AP test?
3 hours.
So you probably can.
Why did I go that way? All right. So I've been trying to write this so you could have plenty of practice, but it's tricky because the formula, where is it? Right here. That's how you do it. But I can't type it right. Like I'm missing. Anyway, it's a tricky problem. And it's way tricky to try and type it out in one step. That's the formula of how you would find the answer, how a computer would find that. I was able to program the other ones, but I cannot get this one to click.
Wait, do you always do plus or minus 2 on your answers?
No, not always, but on those I did. Yeah.
So is that open yet or no?
It's not open, and it probably won't be because I switched it. Hold on. Okay, so we all are aware I'm kind of nerdy,
Yeah.
but when you're good looking, it doesn't matter, right, boys? Half of you are the exact same. All right, so I started writing this, and I love it. Actually, I really enjoy this stuff, trying to figure out how one of our this is a double picket fence, and then a whole different equation. So anyway, that's how you do it. Oh, I'm jazzed, but it won't work. It's really tricky. So I switched it up, and you guys are free to you're free to already go to this. This is open. I just did it in a spreadsheet instead. Now it might seem confusing, but if you go chapter 11 through 13, free response test help, it gives you a practice problem. It gives you the video of me doing it. Then it says, now try your own. And it gives you the same question, but it says you pick a number. And then a density of you pick a number. And it asks you to do these things. And then you go here. And all you'll do is you'll put your 2 numbers you chose there. And then it tells you all the parts. So it's kind of the same. It just doesn't auto grade for you. Because look, to find the mole fraction is just H5 over L5. But this is super nerdy. So that would be that equation, but that involves A4 and B4. and that equation, which involves A4 and B4 as well. So when you try and type it all in, it's a nightmare. But if you do it in a spreadsheet, it's pretty easy. What's that? Right here? Because there's no values here yet. This formula is trying to take these two numbers and divide them, but they don't exist yet. If you ever, when you do this, I hope you will for sure use it. There's a practice for percent concentration. There's one for boiling point. You switch sheets, and there's one for vapor pressure. You will find the answers. So if I put in a like 25 or 50, whatever, and a 1.1, then those three numbers, these are the answers to what you would have calculated, these three answers on your paper. These are just values that help us find those. You don't need to worry about those. Whatever, you don't, most of you don't care. Oh,
so you're just like
going this way.
like a math formula you have to plug in to fix the test, to make the test right. Or wait, what?
It's don't even worry about it.
You confuse the rest of us more than
What's going on?
Just
That's what I was asking Cooper, and I didn't get any further than you were.
It's just.
I forget who I'm dealing with.
Ouch, that hurt.
Okay, look,
Ouch.
on the test, you'll have a problem that asks these exact questions.
Oh, so 3 response test count. That's probably a good taking of it.
I would. Then there's a video of me walking you through how to do every piece of it. I did this last time too.
And like this will be on the test.
This is exactly on the test.
This is exactly, the last one was like, it's not changed numbers from this.
Well, of course it'll have a different number.
Oh, okay, yeah.
Oh man, we're wasting so much time. Okay, so you read this, you try it, and then you watch the video. And then you're like, okay, now try your own. And you pick your own numbers and try them. And then, let me finish for freak's sakes. All right, then you solve it with your own work, and then you go to the spreadsheet, put the three numbers that you put in to check your work.
I got you.
Okay.
So the spreadsheet does tell us our answer.
I get it.
Yes.
To help us.
Yes. Yes. Yes, sir.
Okay, so